Hi everybody, my name is Greg Hancock, and along with my seasonal allergy-affected friend Patrick Curran, we make up Quantitude. We're a podcast dedicated to all things quantitative, ranging from the relevant to the completely irrelevant. In today's episode, we talk about Sewall Wright's path tracing rules as an alternative to covariance and matrix algebra, how the rules work, and the tremendous insights they can provide toward understanding a model. Along the way, we also mention the Unabomber, crate and barrel, grocery lane profiling, tedious as poop, throwing dead cats, senior animal husbandman, using your fingers, creepy guy in an alley, sweatpants versus suits of armor, getaway car drivers, hold my guinea pig, chalkboard contests, western Kansas, and getting tased. We hope you enjoy today's episode.
So I got to tell you, spring has sprung in North Carolina, and how you know that is my eyes are swollen shut, and I'm on this bad trip of Flonase, Claritin, and Benadryl, ensconced in coffee. I'm in a t-shirt, I'm in shorts and bare feet. I have my feet up on my desk. I'm pouring new coffee. I would have to say, looking at you as we speak, you appear to be wearing multiple hoodies and are shivering. And have gloves. All right, now you're just looking like the Unabomber at this point. Although the Unabomber with a lovely hutch behind you with kitschy collectibles.
Isn't that nice?
So the Unabomber after going to Crate and Barrel.
Right.
Is there some story behind this?
Well, I am in Ohio, where I come to help out with my elderly in-laws from time to time. And I stay upstairs here, but unfortunately the furnace has died. And outside, it's currently 21 degrees Fahrenheit, which is like minus 6 degrees Celsius for our friends elsewhere in the world. In the bedroom, the top temperature is 45 degrees Fahrenheit, which is around 6 degrees Celsius. So right now, I'm upstairs just shivering to the bone. I may have to go get a blanket here.
Yes, he's shivering and needs a blanket. And for our friends elsewhere, that means he's whining like a big baby.
Whatever.
Jeez, just suck it up and get to work, dude.
But anyway, I'm here helping out, and I will go to the grocery store in a little while. The grocery store here, there's one lane, unlike at home where there's like 8 lanes. And I don't know about you, I have this habit of looking to see which lane I should be in all the time. And then sometimes I'll zip over to another lane because I think it's moving faster, try to figure out the average age of the customers in line to see which one might move faster.
You're profiling. That's what you're doing. You're lane profiling.
In full recognition of the fact that other people are doing that to me. But invariably, you know, what happens is I look back at the lane that I moved from, and I would have almost always already been through the lane if I had just stayed where I was.
Oh, it's an absolute rule.
Yeah.
You change lanes in heavy traffic, and the guy behind you is going to pass. It's a law of life.
I used to drive my dad a lot of places, and my dad was just the sweetest, quietest, most patient guy. But he got so mad when we would be out driving. And I remember I was driving him someplace one time. He was in the passenger side. We were on the Baltimore Beltway, and we were at a standstill. And this guy in a truck was just weaving in and out of lanes, going up on the shoulder, coming over. And my dad's in the passenger side, just so angry at that guy who seemed to be taking advantage of the system, and all the injustices of 80 plus years come to that moment for my dad. And eventually, when we make it up a little bit farther on the Beltway, we're sitting right next to that guy. And my dad realizes that because the guy's truck is unmistakable. It's a hot day. You know, I've got the window down. And my dad, from the passenger seat, leans across me, flips the guy off, and goes, "You f***ing And I'm like, Dad, you can't do that while I am driving. Again, really mild-mannered, peaceful guy, and I really don't want to have a throwdown on the side of the Baltimore Beltway. But I just like the justice of the fact that the guy had been all over the place, and in the end, you know what? He's just right next to us.
All of us at one point or another have thought, hey, I got a shortcut. Hey, there's an easier way of doing this. And then it turns out to be 10 times harder than if we had just sat down, rolled back our sleeves, and done what needed to be done. And that's kind of what we're going to talk about today.
It is. And for all these shortcuts, they really turned out to be long cuts. let me just say that there is one shortcut that I think is infinitely better than the long cut or whatever. And that has to do with a little corner of our world of structural equation modeling. So without giving it away yet, although I think we gave it away last week, in structural equation modeling, the way you and I practice it, it is also historically referred to as covariance structure modeling, because so much of what we do is try to propose a model that explains why variables covary the way they do, or why variables vary the way they do as a whole system. So there are a lot of moving parts just in this covariance structure, not to say anything of an accompanying mean structure that we could get into. But even if we simplify that and say rather than variance and covariance, even think about it correlationally. You've got a whole system of, 20 variables, 30 variables, however many you might have. And we ask, why do those variables correlate the way they do? I mean, you've got this monster of a model sitting there right in front of you. That's a lot of moving parts to try to think about and keep track of.
You know what's interesting, Greg, is there are different ways that you can think about these models, even though they all are doing exactly the same thing.
Yeah.
There are some black box kind of instruction out there where it's like, look, don't worry your pretty little head, but here's your model, here's your chi-square. Do everything you can to get an RMSEA of 0.049 and you're off to the races. So kind of model A. Model B is a little bit like I was born and raised, which is starting with what are called path tracing rules. And that's what we're going to talk about in this episode. That's going to be our shortcut that has a lot of glorious advantages. And the third one that we can talk about briefly here, which is covariance algebra based. For those of you who haven't been exposed to this, covariance algebra is a flavor of scalar algebra that we talked a little bit about in the first matrix episode, but it is with random variables. So certain new rules apply. And Dave Kenny in his 1979 book has a really wonderful chapter on this. Ken Bolin in his 1989 book has 3 or 4 pages that are very, very clear. So what we're trying to do in SEM is parameterize our model in a way that reproduces our variance-covariance matrix as closely as possible with respect to what we observed in the sample. Now, means also come into this, but we'll focus on variances and covariances here. Now, picture a model where you have 2 predictors, x1 and x2. Now, picture in your mind, you have cov, C-O-V, paren, x1, x2. Well, what's the covariance between x1 and x2? Well, it is the covariance between x1 and x2. It takes on the sample value because it's not a dependent variable.
Yeah, the model's not trying to explain why they covary, just allow them to.
Now picture y1 and y2. All right, now they're both dependent variables, and they can be dependent in any way that you want. Maybe they're indicators on a factor, and maybe they're in a path model where you have different predictors. But now picture cov y1, y2. Well, we can actually write an equation for y1, and we can write an equation for y2.
So the basic idea here is that if y1 is a function of other things and y2 is a function of other things, then how y1 and y2 covary will be a function of the characteristics of those elements that went into making up y1 and y2.
And like any good mathematics, there's a set of rules. There are different ways of presenting it. Again, I really like how Dave does it in his correlation and causality book. He has a whole chapter on covariance algebra. But when you lay out these rules, then you can take this covariance between these two, what are now equations, y1 expressed as a function, y2 expressed as a function, and you can distribute things, you can factor out things, things go away, and then you're left with what is the model implied covariance between y1 and y2, given how you structured your own model. All right, that's what SEM is doing. It's doing this covariance by covariance, variance by variance. It's freaking tedious as poop, is the technical term.
Is poop tedious?
Poop can be very tedious.
That is a new level of disclosure.
Now, to be super clear, you get such a good understanding of what the model is doing. It is absolutely beautiful. What it didn't do for me was give you that 30,000 foot visual, though.
Totally.
You're saying this variable that lives way over here in the model is actually correlated with this other variable that lives way over in this other part of the model.
Yeah.
And you can do that through the covariance algebra, but I'd rather use my fingers.
Exactly right. This is an example of where we can get really good at doing things in the weeds, right? That's what these rules are, these covariance algebra kinds of rules. But it's so easy to lose sight of what you're doing. So when you say you want to use your fingers, I love that, because to me what you're saying is you actually want to start touching what's going on in the model so you can understand it a lot better.
Exactly.
And so we're going to go back to really the early 1900s, over 100 years ago. And over the summer, you and I talked about Sewall Wright. And Sewall Wright laid the foundations for all of this stuff. And I think some of the ideas that he had very early on, which we could look at as very elementary, I think they are as insightful as hell and really worth resurrecting, because I think people aren't exposed to some of his foundational ideas that really help you to touch and understand what's going on in any model.
And to do that, I think we can go back to our friend, the path diagram.
Oh, I love them.
I know, right? One of the beauties of SEM is it is so amenable to a visualization of what we're trying to do. SEM just lives within a path diagram.
All right, so to make sure that everybody's on the same page here, let's just talk about the basic building blocks of these path diagrams. And honestly, if just about anybody out there goes to a journal in their field and throws a dart at an article and then opens it up, you're probably going to find some version of a path diagram. And the path diagram is going to be a way of communicating your beliefs about a system of variables. And some of those variables might be measured, some of them might be latent. When there is a box represents a measured variable, something that you observe, something that if you go to your data file, you actually have scores for people on. There might be some missing data, but you have scores for them. So things in boxes, rectangles, squares are going to represent measured variables. And how we connect those will reflect our particular beliefs about how they're related in whatever mechanism we think is operating. For some of you out there, you might not refer to those boxes as variables. You might call them nodes. You might call them vertices. For our purposes, we're going to use the traditional path tracing language and refer to those as variables. And then how do you connect those variables? Well, there are two types of connectors that we tend to use in the system that we're talking about. One is a one-headed arrow, a single-headed arrow that communicates your belief about causality, that the variable at the beginning of the arrow is hypothesized to have a causal bearing, a direct effect on the variable at the other end of the arrow. We call them arrows or paths. Sometimes they might be called edges or arcs, but we're going to refer to them here as single-headed arrows. And the other type of connector then is a two-headed arrow. A two-headed arrow does not mean that you think the two variables at either end have an influence on each other. A two-headed arrow means that you have a theoretical reason to believe that two variables are related to each other, but not because one causes the other. It's usually because there is some mechanism outside the model that you believe is operating to give those covariation or correlation. When we start to get a little bit more daring and believe that there are variables operating out there that we don't have direct access to, we introduce circles or ellipses, and those represent our latent variables, things that we can't see, but we really think that they're an integral part of the mechanism that's operating, a part of the explanatory mechanism as to why the variables we are able to observe, that we are able to hold in our hand, actually correlate with each other or covary with each other. So we have boxes and we have circles and we have single-headed arrows and we have double-headed arrows. There is another symbol that creeps into these models. In fact, plays a really, really important role in some of these types of models, and that would be a triangle. Usually a representational convention for being able to bring the mean structure into our model. So when we're not just interested in understanding how variables vary and covary or correlate, but are interested in the amounts of those variables, then a triangle, which often has a 1 sitting inside it, allows us to be able to model intercepts and means associated with both measured variables and latent variables. We are not talking about those here in this particular episode, although the path tracing that we're going to get into can have implications for and relate to those kinds of things. We're going to keep it at the level of the covariance or correlational structure that we've been talking about so far.
All of us, to varying degrees, are familiar with path diagrams. As Greg said, you would throw a dart. For some reason, I tend to throw dead cats. Is you throw a dead cat at a journal, and there's a path diagram.
No cats were harmed in the making of this episode.
Well, there are huge advantages to these. What is often used, and I would say almost exclusively used in applied work, is a path diagram is used to convey the substantive model of interest. What are the predictors? What are the outcomes? What are indirect effects? What are latent factors? And this is a brilliant use of these. And indeed, I think that a path diagram is often what makes SEM so much more accessible in an applied setting. You can see what your model is implying from a substantive standpoint. But I feel like there are several generations of researchers who, for various reasons, didn't get that same training, that these path diagrams, when properly constructed, are actually isomorphic with the equations that define the model. That is, if you have a properly defined path diagram, that implies the equations that govern the model, and the equations that govern the model define the path diagram that goes with it. You can go back and forth. But maybe the most magical thing goes back to the 1920s, that using boxes and arrows and circles and using our two index fingers, we can use a set of tracing rules that gives us the covariance algebra for every model implied relation in our set of observed variables. It is freaking magic. I had a really funny experience where Ken Bolin and I years ago were working on a project together, and we were up on a big chalkboard. It wasn't even dry erase. It was just an old school chalkboard. And we were trying to figure out the identification of a model. And on the left-hand side of the board, he was doing the covariance algebra. And on the right side of the board, I was frantically doing path tracing rules. And we were having this almost race, and it was just really funny as I've got my index fingers as I'm tracing through this really complicated model. And I don't teach that to my own students. So I met with a student not long ago who had a complicated model and it wasn't fitting, and they had this big modification index that indicated a misspecification. And I looked at the path diagram and I said, well, look at the tracing rules. The variable wants to go through here, but you're not allowing it. And they looked at me a little glassy-eyed and said, I'm sorry, I don't know what tracing rules are. And I'm like, oh my God, who taught you SEM? And they looked at me glassy-eyed and said, yeah, it was you.
All right, well, this is your time to atone then. Let's go.
Oh, no, I don't atone.
No.
No, I'm sorry.
Okay.
So why do we care? Because if you have parental substance use disorder at the left-hand side of your path model, and you have adolescent substance use way at the right hand of your model, and you have a field of mediators in between the two, path tracing rules let you understand all the ways that the parent predictor is influencing the child measure as it travels through this set of observed variables.
Right.
So as every listener is fully aware, this entire arc of conversation inevitably leads us to guinea pigs.
Obviously, it's all about guinea pigs. So for those of you who didn't listen to our summer episodes, first of all, shame on you. Shame on you.
Anyway, guinea pigs.
Guinea pigs, yeah. So path analysis, or as it was called, the method of path coefficients, was developed by Sewall Wright. And we talked about Sewall Wright a bit in the third of our summer episodes, the Summer of Love episode. I know how you like that. So I'm not going to go back and rehash everything that we talked about there. But if you want to know why Patrick is talking about guinea pigs, and even more why he could have said guinea pig fetish, then you should go back and listen to that.
For Wright, not me. Can we please clarify that?
Sewall Wright developed this method of path coefficients in the 19-teens, actually, and codified it really, really nicely in a paper in 1921 and again in 1934. His title when he was writing, which I love, was that he was the senior animal husbandman in animal genetics at the Bureau of Animal Industry in the United States Department of Agriculture. That was his title. And in the first paper that he wrote in 1921, here's the setup that he gave. The present paper is an attempt to present a method measuring the direct influence along each separate path in a system, and thus of finding the degree to which variation of a given effect is determined by each particular cause. The method depends on the combination of knowledge about the degrees of correlation among the variables in a system, with such knowledge as may be possessed of the causal relations. So he was coming up with a system for you to understand, for you to keep track of, for you to reckon why variables correlate the way they do, and in some cases don't correlate at all.
And this was 100 years ago. This is the genesis of a set of heuristics, of rules, that if you lay this out in this particular way in terms of a path diagram, if you do the following, this is what your model is implying. It's really a remarkable work.
It is beautiful. And he came up with what have come to be called Wright's rules, or Wright's rules of path tracing. When I went through his work, I didn't find them so clearly articulated as they are now. It wasn't like they were buried in a footnote like Spearman did, right?
Spearman, the invention of factor analysis.
Footnote to table 6 or whatever it was. Yeah. But if you go through and you read Wright's stuff, you can pull out these particular rules, and they have been tightened up over the years.
Again, going back to Dave Kenny's book, Correlation and Causality, he has a chapter on covariance algebra, and then he moves into path tracing rules. And Dave has a beautifully concise and elegant statement about these tracing rules. Dave focused on standardized effects, so correlations. Now, all of this stuff scales up to variances and covariances, but we're going to focus on the standardized like Dave did. So here's out of his book. The tracing rule is a simple non-mathematical rule. The correlation between x sub I and x sub j equals the sum of the product of all the paths obtained from each of the possible tracings between I and j. The set of tracings include all the possible routes from x sub I to x sub j, given that A, the same variable is not entered twice, and B, a variable is not entered through an arrowhead and left through an arrowhead. That's it. That is the distillation of Wright's tracing rules for standardized effects.
So you pick any two variables, and we ask, why do those two things correlate? And what Wright said and what Kenny really nicely crystallized is that how two variables correlate are going to be a function of different ways in which those variables are connected in the context of your path model. And these rules lay out what will define those legal ways. So help us get into this.
Okay. What we're doing here is you're looking at your path model, whatever it might be. It might be a 3-mediator path analysis. It might be a bivariate latent growth curve model. Mm-hmm. And what we're going to do is progress science through index fingers. So everybody hold up your left index finger, unless you're driving. Everybody hold up your right index finger.
Like you haven't driven with your knees, please.
Yeah. Never mind. What we're going to do is walk up to the whiteboard with our index fingers, and we're going to put one finger on one variable, and we're going to put another finger on a second variable. And path tracing rules are going to allow us to rebuild the model-implied correlation between those two variables. Now, we could do it with covariance algebra. We could do it with matrix algebra, but we're going to do it with our fingers.
Yep.
Now, use whatever analogy you would like. I love the Odyssey. All right, so what we're going to do is we're going to hold one finger still, and the other finger is going to travel to meet it. It could be Odysseus. It could be Milo and Otis, if
No.
you like Disney.
Milo and Otis. They're traveling far away from home, and the only way back is together.
No, not Milo and Otis again.
It could be the Wizard of Oz. Dorothy is trying to get home.
There's no place like home.
What do you got, Hancock?
How about Patrick trying to get back to his dorm room during college on a Saturday at 3 a.m.?
Okay, we're not going to get that complicated.
Okay, this is much simpler.
This is a much simpler problem than that. Anyway, you've got one finger on one box and one finger on another box, and you want to get from one to the other. One finger is going to stay still, the other finger is going to move. We can expand Wright's rules and Kenny's rules just to be a little bit more explicit in the things you can and can't do. Now, let's not forget our motivating goal. What we want to do is do a trace, and along that trace, following these rules, we're going to pick up coefficients. Maybe they're regression coefficients, maybe it's a correlation, but as we go along a trace, we're going to gather those together and multiply them together. And the product of all of those coefficients is going to represent that first trace. Now, depending upon the model, that may be the only trace. But there might be another trace to get from one variable to the other. We're going to pick up the coefficients along the way and multiply them, and we're going to add that to the first trace. And we're going to do that for all the traces that are possible following the rules.
Yeah, two variables can correlate for more than one reason, and that's what we're tracking here.
All right, so I'm going to do a couple of rules, and then Greg can do a couple of rules. So we got a finger one place on the board, we got a finger on the other place on the board. We're going to hold one finger stable, and the other one is going to be trying to find their way back home. Rule number one, and we're going to start by saying depending on the trace, because this depends on the characteristics of the model and what you're trying to achieve. You might choose to start going forward with your finger. All right, so my left hand is on a box, my right hand is on a box, and I'm going to start moving forward down single-headed arrows from one box to the next box, moving forward. You can do that. You know what? You can go forward as many times as you want. You know what the problem is? Once you start going forwards, you can't go backwards, and you can't go across a double-headed arrow. So once you're moving forward, you can only go forward, although you can go as long as you want.
Yep.
But you can't go backwards, and you can't go over a double-headed arrow. All right, so rule number one, once you start going forward, that's all you can do. Rule number two, you might, for various reasons, choose to start going backwards. So what backwards means is that we're leaving a box at the arrowhead, and we're just moving backwards from there. All right, here's what's cool. You can go backwards all afternoon, as many backward arrows that you want. But here's the cool thing. You can actually do one of three things as you're moving backwards. You can go backwards, and if Milo and Otis get back to your finger, you can just stop. All right, so back, stop.
Back, God!
You can go backwards, back, and then you can start going forwards again. Ooh, that's cool. So you can go backwards and then forward, but rule one applies to going forward. Once you start going forward, that's it, buddy. That's all you can do.
Yep.
All right, so you can go backwards and stop. You can go backwards and forward, or you can go backwards and span a double-headed arrow. You cross that double-headed arrow, you can stop, you can move forward again, but you can't go backward, and you can't cross another double-headed arrow.
What I like about these rules is that they completely map on to what makes sense. When you're tracing forward, that's saying that those two variables correlate because of the influence that one has on the other. Direct influence if it's one arrow, indirect if it's multiple arrows. If you are going backwards and then pivot to go forwards, what you're saying is that the two variables correlate because of the spurious influence of the thing that was up there where you pivoted. So these rules map onto the actual reasons that things should be correlating. I'm going to throw a third rule in here, and that is that once you cross a double-headed arrow, or as you say, span a double-headed arrow, you cannot span another double-headed arrow. So if you cross a double-headed arrow, as Patrick said, you can't go backwards after that, and there is no backwards. You can only go forward or stop. One way to think about the idea that you can't go across two-headed arrows in the same trace is just because X and Y correlate, which is what the two-headed arrow is saying, and just because Y and Z correlate, which is what the two-headed arrow is saying, doesn't mean that X has to correlate with Z. If you think about it in terms of Venn diagrams, you could have X and Y overlapping, and you could have Y and Z overlapping, but that doesn't mean that X and Z are overlapping with each other. So in addition to Patrick's rules, a third rule is that you can only go across one two-headed arrow. It's funny, we're taking what was a small set of rules and we're making them a bigger set of rules, but I'm hoping that that makes it easier to follow as we're doing this on the podcast. So the next thing that I want to say is that as you are trying to get that one finger back home, you can only touch a variable once in that trace. So if there's anything about the trace and you say, but I followed the rules, I only did this, I only did that. If you come back to the same variable as part of a trace, then that is not a legitimate trace. And that is sometimes referred to as the no loops rule. It keeps you from going wee round and around and around in systems where that would be allowed based on the structure of the path traces that you have.
So you can go forward all you want, but nothing else. You can go backward all you want. You can stop, span, or go forward again. And you can't touch the same variable two times in a given trace. All right, those are the core rules. So what do we do now? Well, you do that for all the legal traces. You add them up and wait for it. that is the model implied correlation between those two variables, and that is the expression that you would get if you did the covariance algebra that Bolin is doing to my left. They're the same thing.
They are the same thing, except, and this is a really beautiful except, you can actually see the reasons in your hand, right? You go through all the covariance algebra and you get some stuff out and ta-da, you got the right answer. You go through the path tracing, and this trace might represent an indirect effect, and this trace might represent a spurious association, and this trace might represent something else. So you actually have this beautiful theoretical decomposition of the correlation into things that help you understand why those variables correlate. It's funny, so people who study mediation, really what they're doing is they're just isolating a specific type of trace between a set of variables. And if you go through it at a covariance algebra level or a matrix algebra level, that is buried inside there. So this is stuff people want. It's stuff that helps people understand the mechanisms that are operating.
Okay, so in the spirit of trying to visualize these things, let's work through some examples. And we can start X predicting Y.
Okay.
There are only two boxes on the board. One is labeled X, and it has a single-headed arrow pointing to Y. Put one finger on X, put one finger on Y. What are all the possible ways we could do that? Well, we could start going backwards, and it's Y to X. Well, that's it. We're done. We can start going forwards, right? That's an equivalent way of doing that trace. They're not separate traces. We could go X to Y. Well, that's that relation. Think about when you teach this, or if you've been a student in a class and somebody may have told you at some point, well, in a one predictor regression, the standardized regression coefficient is the bivariate correlation.
That's right.
Well, this is highlighting that. The only way we can get from X to Y is down that single regression coefficient in a standardized metric, which is the bivariate correlation.
Exactly. Let's kick it up a notch. What do you say?
Okay, Hancock, let's have X to Y and Y to Z.
All right. So the first thing that I'm going to say about this is that we're not just talking about one correlation here. We would be talking about what does the model imply about the correlation between X and Y, between Y and Z, and between X and Z. I'll start with the correlation between X and Y. What are all the ways I can trace one finger from X to get to another finger on Y? And the answer is there's only one way to do it. It's just sliding right down that single-headed arrow. So the correlation between X and Y that is implied by this model, just like in the first example we had, is nothing more than that single path, that direct effect. Same thing holds for from Y to Z. If I put one finger on Y, one finger on Z, there's only one way to get between the two of those, and that would be whatever the path value is between Y and Z. Now, the more interesting one is the path that goes from X to Z. We ask ourselves, how many ways can my one finger on X get to my other finger on Z? And interestingly, the answer is there is only one way. It is to go down from X to Y and then Y to Z. What that means is that the model implied correlation between X and Z is going to be the product of the first path and the second path. And Patrick already talked about products as being the way that we aggregate these things within a single trace. And that totally makes sense, right? Because if it were the case that X wound up not having any effect on Y, then X would not have a reason to be related to Z either. So the idea of things being a product, even though it's rooted in algebra and we could show why it's a product, it makes total sense because any one of those paths breaks down, the entire chain winds up breaking down. So the correlation between X and Z is just that thing that we might call a mediated effect. The path from X to Y times the path from Y to Z. Done and done.
You just go forward from X to Z, or you could equivalently start and go backwards from Z to X. Remember, those are not separate traces. Those are equivalent ways of doing the trace. Mm-hmm. But there are a couple of really interesting things from this as well. What don't we have in that path model? Well, we don't have a direct effect from X to Z that bypasses Y. Well, wait a minute. What does that imply? As Greg just said, the only way to get from X to Z is through Y. So it's a total mediation. That effect is completely mediated. Well, we have an over-identified model there. Why? Because we imposed a restriction that X cannot directly predict Z bypassing Y.
That's right.
There's no direct X to Z effect. Well, what are the implications of that? First, we have 1 degree of freedom, and so we have a test of model fit because we've imposed a restriction. And that restriction is we're not allowing that effect to be there. But what else does that mean? Well, as Greg implied, the correlation between X and Z has to be completely reconstructed by the X to Y and Y to Z effect. Well, we have a test of model fit. What if we get a test that indicates, ooh, wow, your hypothesized model does not fit your observed data well? Well, that implies that the correlation that is imposed by the model does not closely correspond to that we observed in the sample. Well, what does that mean? Well, it's whack-a-mole. Right? As we've talked about whack-a-mole before.
That's right.
If there is an X to Z effect and we remove that, that effect wants to be there to reproduce that correlation, but we're not allowing it.
Yeah, I love everything about this teeny tiny example because it illustrates so many things already. You know, what we are saying with this model from X to Y to Z is that the three correlations that those variables have, XY, YZ, and XZ, are theoretically governed by only two moving parts, the path from X to Y and the path from Y to Z. So we're saying three correlations are explained by two parameters. That's where 1 degree of freedom comes from with this model. The idea that we have been, didn't you call degrees of freedom measures of courage?
Yeah.
Isn't that how you refer to it?
Yeah.
That someone was courageous enough to say any potential path from X to Z is 0. That is guts. Saying that there's a path from X to Y or from Y to Z is saying, well, I don't know, it could be something there. I don't know how big it is. Saying that there's no path from X to Z is you going, it is 0. I have no need for that path. And so as Patrick said, that opens up the opportunity for misfit, but it also opens up the opportunity for our model to flex a little bit and say, heck yeah, I can do this. I can explain those three correlations with only two parameters. I got this. So assessing fit and assessing misfit.
And where do you pay the reaper? Remember, folks, you always gotta pay the reaper. Let's say that X to Z wants to be there. All right? So you bellied up to the bar and you took 2 fingers of whiskey and threw it back and slammed the shot glass down and said, I believe the relation between X and Z is wholly mediated by Y. Well, what if it's not? But we force that onto the model? Well, the model is going to try to reproduce that XZ correlation as closely as possible.
Yeah.
If there's a direct effect that you've pulled out, this is how whack-a-mole operates. That increases the potential that X to Y and Y to Z relation is going to try to pick up the omitted X to Z effect.
Yep.
Because it's frantically trying to get the model implied correlation as close as it can to the sample correlation. And you're going to get a biased mediated effect because it's trying to pick up the effect of the omitted direct effect.
Yep, the two path values that you have to adjust are not just trying to serve the relations between the variables at the two ends of those paths, but between the two variables at both ends of that particular model.
All right, buddy, I'm going to shove you harder.
Oh, okay. What do you got?
Picture on the whiteboard, we're going to add a second predictor. So we have X1 and X2, and the two boxes are connected with a double-headed arrow. Why? Because our exogenous variables are allowed to correlate with one another, but we're not saying one determines the other.
Okay.
They are just correlated. So we have two correlated predictors, X1 and X2. Both have a single-headed arrow to Y, and only Y then predicts Z.
Okay.
All right, so it's very similar to our prior one, but now Y is jointly determined by X1 and X2. Walk us through the path tracing rules, because that just got more interesting.
Yeah, so it's kind of shaped like a hand mirror, maybe. You've got this thing up at the top that involves the two X's. It comes down to a point at Y, and then it goes from Y down to the bottom of Z. We got 4 variables, and 4 variables are going to correlate a total of 6 ways. X1 with X2, X1 with Y, X1 with Z, X2 with Y, X2 with Z, Y with Z. 6 correlations that this model is trying to explain, and this model has 4 moving parts. The correlation between X1 and X2, the paths that each of those have into Y, and the path from Y to Z. That's all you got to build what you need here. So if I do my tracing, I can start with X1 and X2. how many legal ways can I get from, let's say, x1 to x2? And the answer is one way. I just trace my little way across that two-headed arrow, that span, and the two are joined together. There is no other legal way. If I take x1 and I go down to y, I have gone forward. I cannot pivot and go back up to x2. So that's it, I'm done. x1 and x2 correlate because the model said they correlate. Done and done as far as they're concerned. With x1 and y, there are actually two ways that I can get between them. The direct effect that x1 has on y, and what's sometimes called the unanalyzed association, where you go from x1 across the two-headed arrow to x2, and then down from x2 to y. That's referred to as an unanalyzed association because it contains a two-headed arrow. It's not unanalyzed in the sense of us not doing the math. It's unanalyzed in the sense that we're not literally modeling the mechanism that's responsible for that two-headed arrow. So two sources of correlation, two legal traces from x1 to y. And when we add those two traces together, that is the model-implied correlation between x1 and y. And you know what? Everything I just said flips for x2 also. There are two ways to get from x2 to y. Now, thinking about how things connect to z, how would I get from x1 to z? Well, there's that indirect effect that goes from x1 to y to z. That's a legal trace. And there's an unanalyzed association that goes from x1 across the two-headed arrow to x2, and then x2 causally to y, and y causally to z. I have two traces that get me from x1 to z. Add those together. That is the model-implied correlation between x1 and z. And there's another one just like it from x2 that mirrors that perfectly, so I won't go over it. The last piece of this puzzle is how y and z correlate according to this model. And I'm torn. Is that easy? Is that hard? Let me think about that for a second. Certainly, if I got one finger on y, one finger on z, I can get those kids together pretty easily by just taking one finger from y and moving it over to z. That's a direct effect, and that is an absolutely legitimate source of correlation between y and z. If I'm sitting on y, though, it is completely legal for me to go back up to x1. That's a legal path. And it is legal for me to go from x1 across the two-headed arrow over to x2. Well, where do I go now? Well, I would come back down to y, and then all of a sudden, warning sirens would go off because I would have touched the same variable twice in my trace. So if I was thinking I was going to take a little stroll around the park up by the x1 and x2, come back to y, and then go down to z, not allowed to do that. So that means that the model-implied correlation between y and z is nothing more than the direct effect that y has on z. And that is a full reckoning of all 6 correlations among the variables as a function of the 4 parameters in this model.
And think about the restrictions we've imposed. This model has 2 degrees of freedom. In the path tracing rules, it's very clear how we're getting those. x1 cannot directly impact z. x2 cannot directly impact z. They can only impact z through their influence on y. So looking at the path diagram and thinking about the path tracing rules, you immediately see that model has 2 degrees of freedom because we've removed those 2 effects.
Beautiful.
Now, when we talk about doing a priori tests of our hypothesized model, our chi-square test statistic is evaluating what is the impact of removing those 2 parameters from the model in our ability to reproduce those 6 correlations. If air quotes it is non-significant, the chi-square, then we're tempted to conclude that we do a pretty good job reproducing those correlations without those 2 direct effects. If it is air quotes significant, we're tempted to say, oof, you know what? The model is implying that we're really not able to reproduce those x1 to z or x2 to z correlations by omitting those direct effects. The modification index is saying, hey, dude, right? The MI is like this kind of creepy guy in an alleyway, and he's like, psst, buddy.
Come here, kid.
I can reduce your chi-square by 8 if you just put that single-headed arrow. Well, that's what it's literally doing, is saying if you were to put the direct effect from x1 to z, then we would be better able to reproduce that correlation. But here's the poke in the eye, is if you put both of those direct effects in, the model is what we call saturated. We have imposed no restrictions, and you know what? We are going to perfectly replicate that correlation because we've saturated every possible way we can get from x1 to z and from x2 to z. So how proud of yourself should you be by being able to reproduce that perfectly? None at all.
That's right. It's not a big achievement to be able to fit into sweatpants because they stretch all over the place. It's a big achievement to be able to fit into a suit of armor, right? The more restricted it is, the more of a test it places on you.
The other thing to highlight is the importance of the correlations among your exogenous predictors. We forget about those a lot of times. It's like, oh, we got our predictors, their demographics, we're controlling and removing for them. But go back a couple of minutes to what Greg described. If we're trying to see how X1 relates to Z, one way is the X1 to Y to Z. But the other one is the X1's correlation to X2 that goes to Y, that goes to Z, right? As these two guys hang out together, they are related to one another. And so what X2 is doing, in part, relates to how X1 is related to Z itself. Now, let's take a model that we wouldn't normally do, but it makes the point. Let's say that X1 doesn't predict Y or Z, that X1 is somehow just hanging out there and is correlated with X2, and X2 predicts Y to Z. The model still implies a correlation between X1 and Z. How? Well, X1 is related to X2, and X2 predicts Y that predicts Z.
Right.
All right? This is like getting arrested for being the driver of the getaway car. It's like, I didn't do it. I didn't hold up the bank. It's like, dude, it's the friends you're hanging out with. And so one thing path tracing rules do is makes us really appreciate how all the variables relate to one another in our model.
I like it.
Okay, wise guy. Things seem easy enough when we have observed variables. Let's back the truck up a little bit and say, what about a confirmatory factor model? So we're going to go up to the whiteboard, and I'm just going to make things up. We're going to have 5 observed variables that load on factor 1, and we're going to have another 5 observed variables that load on factor 2, and we're going to allow factor 1 to covary with factor 2. So we have 5 indicators each on 2 latent variables, and the latent variables correlate with one another. Talk to me about how do we reproduce element by element our 10 by 10 correlation matrix?
You are giving me a 10 variable model to do in a podcast. Is that what you're saying?
And what you're saying is you're going to whine about it.
Oh no, hold my guinea pig. Here we go. I got 5 indicators of factor 1, 5 indicators of factor 2. What this model is saying overall, I'm going to ease into the path tracing in just a second. What this model is saying overall is that the first 5 variables correlate because they're influenced by something in common, a factor. The second 5 variables correlate because they have something in common, that second factor. And the first set of variables, y1 to y5, the second set of variables, y6 to y10, they correlate with each other because the factors that govern them correlate with each other. That's the conceptual orientation. Now, as a path tracer, I am not going to drag you through the, what would it be, like 45 correlations that we have operating here?
10 times 9 divided by 2.
There we go. So I only need to take you through a couple because they stand for all of the rest. If I want to know why y1 and y2 correlate with each other, put one finger on y1, one finger on y2, they are both indicators of that first factor. I just move my finger from y1 backwards up to the factor and forward down along the second path. And what do I have? I have a trace that includes the first loading times the second loading, done and done. There is no other legal way to get between variables 1 and 2. In fact, the correlations among all variables y1 through 5 have that exact same pattern. And the correlations among all variables y6 through y10 all follow that exact same pattern. Up to the factor and down, there's no more tracing that you can do. Every model implied correlation of variables within their respective sets are the products of 2 loadings. Now, if I want to get from a variable that's in that first block, y1 through y5, to a variable that's in the second block, y6 through y10, easy peasy. Let's say I got one finger on y1, which is the first indicator of that first factor, and I got one finger on y6, the first indicator of the second factor. How do I get between those two? There's only one way to do it. I take my y1, slide backwards up that loading path, pick up that loading, go across the 2-headed arrow, pick up the correlation between the 2 factors, and then slide down that loading path to y6. That's it. There is no other way to get between the two. That means that the correlation between those two is a loading that we could call lambda if you wanted, across the correlation between the two factors, which we could call psi, and then we could go down the other loading path, which is another example of a lambda. So in that case, the correlation between any variable in the first set and any variable in the second set is going to be a loading times the factor correlation times the loading. In Greek, lambda, psi, lambda.
A couple of things that this then highlights. First, Greg is using the rules. We can go backwards, we can go over a single span, and we can go forwards again. Now, notice that Greg said you go up a lambda, you go over a psi, and you go down another lambda. So what is the correlation between two items on different factors? It's lambda, psi, lambda. One of the most famous matrix expressions in factor analysis is, wait for it, lambda, psi, lambda prime. And then we have plus theta epsilon for reasons that we won't talk about here. But what is that lambda psi lambda prime? When you do that matrix valued function of lambda psi lambda prime, lambda is going backward along that factor loading, psi is going across the covariance, and lambda prime is moving forward along that loading to the other variable. So notice the lambda psi lambda pattern in that. It's exactly doing the path tracing rules at the level of the matrices.
Yeah.
All right, smart guy, I'm going to change a factor correlation to a regression coefficient. Same deal. 5 indicators on the first factor, 5 indicators on the second factor. But now factor 1 has a directed one-headed arrow predicting factor 2. It's a regression coefficient. What are the implications of that?
A lot from a theoretical standpoint, where, in the previous model that was a confirmatory factor model where the two factors correlated with each other, what we were saying was that neither factor causes the other. They likely are related to each other because of some forces that exist outside the model. This model, where you say factor 1 influences factor 2, that took some guts, right? That says that you have a theoretical reason for one of those things to be influencing the other. From a path tracing standpoint, it is not going to make any difference. If I want to know how the first 5 variables, again, we'll call them y1 through y5, how those correlate with each other, it's still just going to involve 2 loadings, tracing from one variable up down to the other variable. Same thing for the variables that are in the other set. So then what happens when we want to get from variables 1 through 5 to 6 through 10? It's the same. Imagine tracing your way from y1 through 5 to y6 through 10. You just go backwards up your loading. You go across the structural or causal path from the first factor to the second factor, and then down the loading path to the other. So all we have really done is replaced what was a factor correlation in our trace previously that Patrick had called psi with a structural path that we could, for example, call gamma. Everything tracing-wise winds up amounting to the same thing.
And once we're at this model, this is a structural equation model. We have multiple indicators on one factor. We have multiple indicators on another factor. We're regressing the second factor on the first. Now we're off to the races. Have a third factor, and what we started with 15 minutes ago of x to y to z, well, now you have factor 1 to factor 2 to factor 3. Everything scales up exactly the same. Picture a crazy complicated model. Because here's where Bolin ultimately won that contest we had at the chalkboard. Because one of the challenges is in complicated models, you have to figure out all the legal traces.
Yeah.
And in a complex model, there might be 6 or 7 or 8 different traces that go into that component.
Yeah.
But you know what? Tough crap.
Yep.
That's what the model is implying. What I mean is that's the point of path tracing, is sometimes what you think is part of the model that's way out in western Kansas that nobody's ever been to before, that actually relates to how 2 variables are correlated downstream. Because Milo and Otis get thrown in a box and dropped in a raging river, and they go all the way out to Kansas and then come all the way back. And that long trace is part of what your model is imposing about how the variables relate, not only from a statistical standpoint, but from a conceptual, substantive, theoretical standpoint.
Apologies to people in western Kansas.
You know what? Is I have gotten 2 or 3 speeding tickets in western Kansas. One of which a state trooper asked me if I was able to read. I was taking exception to the ticket.
It's always a good strategy to take exception to the ticket.
Especially if you like getting tased.
Officer, I have a couple of questions about this. But yeah, Patrick is exactly... It doesn't matter how damn big the model gets. It just doesn't matter. Patrick and I routinely work with people who might have 60 variables in a model. They are all over the whiteboard. The same rules apply. Why does each pair of variables correlate? You just go from one to the other. And that is what's under the hood. Whether you express it in matrices, whether you express it in covariance algebra, whether you do it as path tracing, those are the mechanisms under the hood. Those are the model-implied correlations. Those are the reasons variables relate the way that they do or don't relate. Those are going to be the sources of your fit. Those are going to be the sources of your misfit. It's just a beautiful system.
And it makes you so appreciate the fabric of how all of the variables relate to one another. So I met with a student who had a very complicated model, and they were getting these residuals among their observed and model-implied covariances at the end part of the model, the distal dependent part. And I made a comment about, well, you may have misspecified some of your predictors. And they kept insisting, no, but those aren't involved in this. Those are over in this part of the model. And when you do the path tracing and you see, oh, holy cow, I can go back over this exogenous covariance, then forward. Oh my gosh, they're integrally related to how your dependent variables are related with one another.
Yep.
So why then are we talking about this? Well, there are some advantages just to reiterate as we head toward the exits here. The biggest one is just developing this understanding of how every pair of variables in your model relates to one another. And in the covariance algebra and in the matrix expressions, that is not always as salient as it is when you take your two fingers and say, what are all the ways I can get from one finger to the other finger?
Yep. It's probably quite clear that I love path tracing. I love it for some of the reasons that we've talked about, that it helps us to really visualize all the sources of why variables are related. It also helps to tie together lots of ideas that exist elsewhere. So certainly that these ideas go on to the unstandardized model where we talk about decomposing why variables covary specifically rather than just correlate. We can decompose variances, all of those things. But all of those damn formulas that you had to remember throughout all of your statistics classes, for example, you might have had to memorize the formula for a standardized regression coefficient in a two-predictor model, or the formula for a partial correlation, or a semi-partial correlation, all of those things. And they existed as these separate things that you had to commit to memory. And what I will tell you is that all of those things are just path tracing, every last one of them. If you want to understand how a partial correlation works, all you have to do is draw the picture for it, and the formula for a partial correlation just falls out of the path tracing. Same for standardized regression coefficients as a function of other aspects of the model. The variance of a composite of a variety of variables, that is just path tracing. So I love it when the world distills down to just a few very simple rules that govern everything else. And path tracing is just one of those elegant things that helps you understand so many other things.
So when Ken was doing the covariance algebra and I was frantically trying to find all the possible traces through the path diagram, it did seem like a shortcut that turned into a lot more work. But oh my gosh, we have this model-implied correlation between these two variables. Here are all the components that are contributing to that. And here is what it implies for your theory and your research hypotheses is I know this thing is way over on the left, and I know this other thing is way over on the right. But this is how your model is saying these two relate to one another.
If you don't mind now, I'm going to go sit where it's a lot warmer. Please?
Sure. Let's wrap up with it being about you.
Yeah, before I remove my mitten, can you guess which finger I'm holding?
As always, everyone, thanks for your time. We hope you've had half as much fun as Greg and I have had.
All right, everybody, take care. We'll talk to you later.
Thank you so much for listening. You can subscribe to Quantitude on Apple Podcasts, Spotify, or we'll come over to your house and do a live episode. Seriously, it has been a really long 2 years. And please leave us a review. You can follow us on Twitter, we are @QuantitudePod, and check out our webpage at quantitudepod.org for past episodes, playlists, show notes, transcripts, and other cool stuff. Finally, you can get Quantitude merch that is quite frankly ideal for all of your April Fool's Day gift-giving needs at redbubble.com, where all proceeds go to donors choose to support low-income schools. You have been listening to Quantitude, the podcast equivalent to Western Kansas. Quantitude has been brought to you by the Kansas State Board of Tourism, who would like to extend Quantitude a warm invitation to visit the great state of Kansas and personally embrace the state motto Ad Astra per Aspera, which in the current context loosely translates to Quantitude can and then bend the barbed wire to in the while placing the red-hot horseshoe firmly on their and finally they can with in both of their Kansas. To the stars. By Unstuck in Time, a new plugin for Outlook that manually modifies the timestamp on any email sent during a Zoom research talk, so you can at least maintain the appearance that you're not working while someone is generously sharing their time with you to discuss topics that are important to them. And by Patrick's turn to do the sponsors, which are distinctly Jiffy free. This is most definitely not NPR.